Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. This video is about directional derivatives in terms of the gradient. So, first we will define what is the gradient and then we will talk about its relation with the directional derivatives. So, if you may remember that a few videos ago when we defined directional derivatives, we found them hard to compute, not very hard, but nevertheless they involved some limits which we had to compute. And towards the end I said there's often an easier way of computing them, and the way to compute them involves some hypothesis called continuity, which is why we studied continuity. So, now that we know what is a continuous function, we will talk about directional derivatives again once we have talked about the gradient. So, the gradient is a very important idea and it will be used extensively in the machine learning course that you will see later on. We will also have use for it in the material that comes later. So, let us recall first. So, unless specifically mentioned otherwise, in this video a function will mean a scalar valued multivariable function. So, when I say function, by default that means a scalar valued multivariable function. We will have occasion to use vector valued functions in this video, but on those occasions I will specifically mention that. If A tilde is a point in R n, then an open ball of radius r around A tilde is the set defined as those points x tilde such that the distance between x tilde and A tilde is less than r. So, that is an open ball of radius r. And finally, let us recall that E1, E2, En is the standard ordered basis of R n. So, these are all notations we have been using for a while now, and we will continue to use them in this video as well. Let us recall partial and directional derivatives. So, if f of x1 x2 xn is a function defined on a domain D in R n, the directional derivative of f in the direction of the unit vector u. Remember, u is, we always think of unit vectors when we talk about directional derivatives, at least when we want to actually find them. So, this is the function denoted by f subscript u of x tilde, and it is defined as f subscript u of x tilde is limit h tends to 0 f of x tilde plus h times u minus f of x tilde divided by h. So, the expression in the bracket that is x tilde plus h times u, that is addition in R n, which we know because both x tilde and u are vectors and h times u is scalar multiplication. So, we have we are very familiar with what that means. So, its domain of course may not consist of all points in D, because this limit may not exist at all points. We have seen examples like that. So, its domain consists of those points at which the limit exists. So, at other points we do not talk about this directional derivative, we will say it does not exist. In particular, you can take the unit vectors, u is E I. So, these are the standard basis vectors, and when u is E I, then the directional derivative is exactly the partial derivative of f with respect to the ith variable x I, and we have a special notation for it, which is f subscript x I of x tilde or del f del x I. And both are useful in different contexts. Fine. So, this is a recall of partial and directional derivatives. We have studied these in previous videos. Let us recall also a computation of these. So, if you have f of x y z is x y plus y z plus z x, let us compute the directional derivative with respect to a vector u1, u2, u3. So, this is a unit vector. So, let us compute what is f u. So, f u of x tilde is by definition limit h tends to 0 f of x plus h u1, y plus h u2, z plus h u3 minus f of x y z divided by h, which is limit of h tends to 0 x plus h u1 times y plus h u2 plus y plus h u2 times z plus hu3 plus z plus hu3 times x plus hu1 minus xy plus yz plus zx divided by h. We have actually done this computation in the previous video, but I want to do it again just to recall how difficult it is to compute a directional derivative as of now. So, if you look at what happens to the numerator, several terms get cancelled. So, x times y, y times z and z times x get cancelled, but all the h terms remain. So, we have some h terms with h squared. So, for h squared we get u1 u2 plus u2 u3 plus u3 u1, and then we have plus h times x u1 plus x u2 plus y u1 plus y u3 plus z u2 plus z u1 plus x u3, right. So, I will suggest you check this. There is some symmetry in this, that is why I could write it so easily, which is limit, if you take the limit as h tends to 0. So, h and h cancels, and what you will get is h times this expression here, plus this entire expression, which I will rewrite x times u2. I actually want to rewrite this in a different way. So, let us take the coordinates. So, u1 times y plus z plus u2 times x plus z plus u3 times x plus y. Yeah. So, if you write this down yourself, you will see that this is exactly what you get. So, as limit h tends to 0, this term here becomes 0, because everything inside is a constant with respect to h, and h goes to 0. So, this is 0, and the other term does not have an h. So, it is just whatever it is. So, the net result is this is u1 times y plus z plus u2 times x plus z plus u3 times x plus y. So, we have computed this directional derivative, but notice that this was a fairly non-trivial computation, and this is a fairly easy function. It is a polynomial function. In fact, it has degree just 2. So, even for such an easy function, it took us some work to compute what is the directional derivative. Contrast this with the partial derivatives, which we can write down in a jiffy, right. So, f x is treat x as a variable and y and z as constant. So, if you do that, you get y plus z. F y is treat x and z as constants and y as a variable. So, you get y plus z, and f z is treat z as a variable and x and y as constants. So, you get y plus x. Okay. So, the point here is, which is the title of the slide, directional derivatives versus partial derivatives. Partial derivatives are fairly easy to compute, because we have this very nice way of interpreting them in terms of usual derivatives, meaning one variable derivatives, by treating all the other variables as a constant. Whereas, for the directional derivative, I have to really sit and compute the limit. Okay. Now, I will ask you to observe one important fact here. So, notice these coefficients, and so this y plus z is exactly what you get as the coefficient of u1. This x plus z is exactly what you get as the coefficient of u2, and this x plus y is exactly what you get as the coefficient of u3. So, maybe there is a relation here between the directional derivatives and the partial derivatives, which we can exploit, and which will make computing partial derivatives easy, and that is what this video is about. So, the main upshot is partial derivatives are easy to compute, directional derivatives are maybe not so easy to compute, because you have to actually sit and compute the limit, and that maybe there is a relation we want to exploit. Fine. So, to do that, we have to define something called the gradient vector or the gradient function. This is an exceedingly important function or vector, So this is an idea you must understand, because you need to know this well to carry forward, not just in the next videos in this course, but in the next courses as well. So let us define what the gradient vector or the gradient function is. So suppose f of x1, x2, xn is a function defined in a domain D in Rn containing some open ball around the point A tilde. Suppose all the partial derivatives of f at A tilde exist, okay. Then the gradient vector of f at A tilde is the vector where in the first coordinate you put the partial derivative with respect to x1 at A tilde, in the second coordinate you put the partial derivative with respect to x2 at A tilde, and in the ith coordinate in general you put the partial derivative with respect to xi evaluated at A tilde, and you form the corresponding vector. So, this is a vector in Rn, it has n coordinates. So, this is a vector in Rn. So, when you evaluate, since we are evaluating at this point, these are all numbers, and so this gives you a vector in Rn. So, this is an n tuple of real numbers, and so it gives you an element of Rn or a vector in Rn. So, depending on the context, you write it as a column vector or a row vector. Again, I have been using this fairly liberally, which way do I interpret vectors, as columns or rows. Often we did it as columns, but sometimes I have also run it as rows, and the same thing will apply to this vector as well. So, depending on whether you write in the context Rn as row vectors or column vectors, you will write the gradient vector as a row vector or a column vector. Okay. Important point is this is a vector in Rn. So, given a point A tilde, we had this function f, which was a scalar valued multivariable function defined on maybe some subset of Rn, some domain in Rn, and out of this, by evaluating at the point A tilde each partial derivative, we have created a vector. Okay. So, now first of all, notation, this is denoted by sometimes this is called del, sometimes this is called nabla. So, it is denoted by del f evaluated at A tilde, and then out of this we can form a function, namely what is called the gradient function. So, this is similar to how we formed the derivative function or the partial derivative functions. So, for each point A tilde you can associate a corresponding vector. So, that association we make into a function. So, the gradient function of f is the function taking values in Rn obtained by associating to every point A tilde its gradient vector gradient f at A tilde, del f at A tilde or nabla f at A tilde. Of course, this gradient function may not be defined everywhere, right, because maybe some partial derivative is not defined at some point. So, the domain of definition for this function is exactly those points where all partial derivatives exist. So, all partial derivatives must exist, and only at such points this function is defined. So, just to emphasize this, this is now a vector valued function. So, we started with a scalar valued function f, and out of that we have created a vector valued function gradient of f or del of f or nabla of f. Typically we say del f or gradient f, nabla f is not often used, although the symbol is actually called nabla. Fine. So, this slide, if it is a bit abstract, let us do a couple of examples. This is really easy. All we have done is taken all the partial derivatives and put them into a vector. That is really all we have done, but let us do some examples just to set these ideas straight. So, f of x y is sine of x y. Well, we know what is del f del x and del f del y. We have computed these earlier. So, del f del x was cosine of x y times y. So, y times cosine of x y. Del f del y is x times cosine of x y. So, the gradient function at x comma y is the vector y times cosine of x y comma x times cosine of x y. And what is the gradient vector at some point. Let us say if I want to compute the gradient vector at 0, 0, then this is, you evaluate this at 0, 0. So, this is the gradient vector at 0, 0, and you can see if you evaluate it, you will get 0, 0. If you evaluate it at, let us say, pi and pi, right. So, then we have so, well, I get a cosine which I do not really know what to do with. So, let us say this is pi and 1, right. So, if I do that, then this is the gradient vector is 1 times cosine of pi, comma pi times cosine of pi. So, this is, so cosine of pi is minus 1. So, this is minus 1 comma minus pi. Okay. So, I hope it is clear what is the gradient function. So, it is a function from R 2 to R 2 in this case, and the gradient vector is just the evaluation of that function at whatever point you want to evaluate it at. Let us do this other example. So, gradient of f here is, so I have to write down what are the partial derivatives. So, in this case the partial derivatives, they are very easy, right. This is 2x, 2y and 2z. So, the gradient function is, you just take these and put them into a vector. So, it is a function from R 3 to R 3. So, the gradient function is a function from R 3 to R 3, and now if I want to evaluate this at some point. So, what is the gradient vector at the point 1, 2, 3? Well, you put those values in and see what you get. So, this is 2, 4, 6. Okay. Let us do this last example, because this is a fairly important example. So, now the gradient function will depend, right. So, we have actually computed the partial derivatives of this function. This was from a previous video, I think the one where we computed partial derivatives. So, let us write down what those are. So, the value, so this depended on whether we are evaluating it at 0, 0 or not. So, if it is not at 0, 0, then del f del x is x cube minus y squared x by x squared plus y squared the whole squared, and if it is at 0, 0, it is 0. So, this is if x y is not 0, 0, and this is if x y is 0, 0. And similarly, by symmetry we know what this is y cube minus x squared y by x squared plus y squared squared. So, if you do not remember this or do not feel uncomfortable with how we got this, please compute this again. So, this is if it is not 0, 0, and this is if it is 0, 0, right. So, that is what the partial derivatives are, which means that now the gradient function is the function x cube minus y squared x comma y cube minus, let me rewrite this better, I want to write this in a particular way. So, 1 by x squared plus y squared squared times the vector x cube minus y squared x comma y cube minus x squared y. So, this is if x y is not 0, 0, and it is the vector 0, 0 if x y is 0, 0. So, there is two things to note here. First of all, since we know now what is scalar multiplication, I have pulled out this common thing 1 by x squared plus y squared squared. So, we can do this even for functions, and you have to understand that what this means is that it is multiplied to each of the components, right. So, we have done this idea extensively when we did linear algebra. So, that still continues to hold here in spite of the fact that these are functions. And the second thing is that the gradient function, it could have this, it is like any other function, it could be piecewise, it could be defined in a different way, it may not be defined everywhere, right. So, all of those things are possible, and it takes values again in R 2. So, this is a function from R 2 to R 2. Okay, so, I hope these examples are illustrative of what is the gradient function and what is the gradient vector. So, before going ahead, maybe we should also ask what does the gradient vector do for us, or what does the gradient function do for us. So, what are these del f del x and del f del y? They are the rates of changes of the function in the on the x axis or on the y axis. So, with respect to x and with respect to y, and when you write these two together as functions, they are saying that at that point you can compare these two, right. These two numbers will, suppose the, let us say at this element 1 2 3, the gradient vector is 2 4 6. So, what this is saying is the rate of change with respect to x is 2, with respect to y is 4, and with respect to z is 6. So, the rate of change is 3 times that for z as that for x, or 2 times that for y as that for x. Yeah. So, basically the gradient vector is trying to tell you, it is keeping track, that is one of the things it is doing, it is keeping track of the relative rates of change between the different variables. That is why we are bunching them together, so that we can compare them. Okay. So, this is an idea that we have seen in linear algebra earlier, which goes back to why do we create vectors in the first place, right. So, this is why this is one of the reasons we have created the gradient vector. It keeps track of the rate of change for all the variables together. Fine. So, now that we have studied the gradient, let us quickly study some properties. These are the same properties that we have studied for directional derivatives. So, I am going to summarize them very fast. So, if you have two functions f and g and a scalar c, if you take the gradient of c f plus g, then that is c times the gradient of f plus gradient of g. So, now what are we doing? We are doing vector addition and scalar multiplication. So, all these three terms here, gradient of c f plus g, gradient of f and gradient of g, are vectors consisting of functions. So, they are basically vector valued functions, and c times this gradient f is a scalar multiplication of that vector valued function, and we are saying that these vector valued functions have this satisfy this equation. So, this is actually saying that you compare coordinates, and in terms of coordinates we have already seen this when we do directional derivatives. So, this is nothing very deep, this is just a rehashing of what we saw for directional derivatives applied specifically to partial derivatives. Okay. Similarly, we can do the product rule, and if we think of the product rule, we can summarize it as follows. So, gradient of f g is g times gradient of f plus f times gradient of g, and similarly we can do the quotient rule. Of course, here we need some hypothesis, which I have ignored for now. So, gradient of f by g is, you pull out your 1 by g squared in the denominator, and then you have g times gradient of f minus f times gradient of g. Now, I want to emphasize, of course, all these three come with some hypothesis, right. You have to know that all these gradient of f and gradient of g are defined, and only then all this makes sense, and then g of x tilde is non-zero, etc. So, with those hypotheses in place. So, the main point I want to make here is that yes, we need some hypothesis, but the main point is this looks very similar to the rules we had for derivatives in one variable calculus. Okay. So, when we had one variable calculus, we said derivative of c f plus g is c times derivative of f plus derivative of g. Derivative of f g is g times derivative of f plus f times derivative of g, and derivative of f by g is 1 by g squared g times f prime plus minus f times g prime. And of course, when we did one variable calculus, I wrote the f prime first and the g next. So, the reason I have written it like this is because here we have vectors. So, I always write the scalar first. This is just convention, there is nothing deep in this. So, the point is the gradient really plays the role of assimilating all the information about the rate of change of this function, and can be thought of as the derivative, right. So, we have note that for multivariable functions we have not talked about the derivative at all, we only talked about partial derivative. So, we only said what is the rate of change in a particular direction. So, essentially we talked only about one variable calculus, we reduced it to checking along lines, which is like one variable calculus. But we can ask globally, is there some kind of a rate of change for this function? Can we define something like the derivative for one variable calculus? And the answer is, if we want to do it so that the properties that we have for one variable calculus hold, then this gradient seems like a reasonable candidate for the derivative, and I will expound more on this later on. Okay, so these are properties of gradients. Fine. So now comes the all important point of this video, and this is what we want to take home from this video. Suppose there is a function f defined on a domain D in Rn containing a open ball around the point A tilde. Theorem: suppose gradient f exists and is continuous. So, this is really why we had to talk about limits and continuity, and is continuous on some open ball around the point A tilde. So, it is not just continuous at that point, but it is continuous around that point as well. So, at all points close by that point. Then for every unit vector u, the directional derivative f subscript u at A tilde exists and equals gradient f of A tilde dot u. This is exactly the formula that we saw for the example that we did earlier. This if you remember the example xy plus yz plus zx, when we did fu, what we got was u1 times y plus z plus u2 times x plus z plus u3 times x plus y. So, this expression here we can rewrite as, so this expression here can be rewritten as gradient of f at x tilde dot with the vector u, right. So, the vector u is u1, u2, u3, the gradient of f is exactly y plus z, z plus x and y plus x, and if you dot, this is the expression you get, okay. And that is exactly what this theorem is saying, that you can compute the the directional derivatives from the gradient and that vector u, okay. So, the main upshot is that difficult computation that we did with limits for the directional derivative is no longer needed, provided we have this hypothesis. So, if the gradient f is continuous, which often happens for many functions like polynomials and so on, then we need not do that difficult limit, we can just compute it directly by this formula gradient f dot with u. So, I want to just make a quick remark about why this holds. So, so what is the the directional derivative? That is limit h tends to 0 f of let us say I do it for two variables, right. So, this is x plus h u1 y plus h u2 minus f of x y divided by h, right. So, in terms of my axis, this is like suppose this is u, badly drawn line, yeah. So, this is the line on which u is, this is your u, and x y is let us say a point here. So, you move your vector and your line. So, you draw this line here passing through, and then you take the derivative along this line, okay. So, now what we can do is we can break this into two parts. We can say this is f of x plus h u1 comma y plus h u2 minus f of x plus h u1 comma y plus f of x plus h u1 comma y minus f of x comma y, okay. So, this is my point x comma y, and then divide by h, okay. If I split this up into two parts, so I get f of x plus h u1 comma y plus h u2 minus f of x plus h u1 comma y by h plus f of x plus h u1 comma y minus f of x y by h. Okay, now let us interpret what these two things are. Let us look at the first one. So, this is saying, suppose this is my point x plus h u1 comma y plus HU2. Okay. So, this is saying let us keep the x coordinate fixed. So, that means look at this line, but let us vary y. Okay. So, this difference as h tends to 0, this is like y is over here and you are looking along this line. So, this looks now like a translate of the y axis. So, it is like you are computing the partial derivative with respect to y for this point here, and then the second one, this second expression. So, the second expression is like you are computing it for this line here. Okay. So, with some little bit of approximation and mumbo jumbo, this is more or less like saying this is del f del y at x plus HU1 comma y. Of course, when you take the limit, x plus HU1 also has to there is a limit here. So, with some mumbo jumbo you can put in that limit as well, and this is actually the partial of x at f of x y, right. And because there is a limit here and we know continuity, we can say this is the same as del f x plus HU1 times y. But now note here that when we did this, here the as h tends to 0, the h thing changed, right, your parameterization changed. So, here you have to divide and multiply by u1, and now you do this. So, now it is like HU1 tends to 0, and so I get an u1 extra, and the same thing happens here where you get a u2 extra, and that is exactly how we get this formula. Okay, let us do some examples and clear out what is going on. So, let us say I want to compute fu at x y. Well, I know I need my gradient. So, I have to first compute the partials. So, this is del f del x is 1, del f del y is 1. That means the gradient is 1 comma 1. So, then this is 1 comma 1 dot with u. So, this is just u1 plus u2, right. So, if u is u1 comma u2, this is just u1 plus u2, and I'll suggest you go back to your video on directional derivatives, where we have computed this, where it was a fairly relatively longer computation and we got the same answer. Okay. This is something that we did just a few minutes ago, but I am going to just emphasize that if we use this formula, this is just a one step procedure. So, this is y plus z, z plus x, x plus y dot with u1 u2 u3, which is u1 times y plus z plus u2 times z plus x plus u3 times x plus y. Right. So, you can see now also why this vector notation is useful, and that dot products are also useful. We have finally have scope to use them in calculus. So, and finally, we have f of x y is sine of x y. So, here fu of x comma y is so we need the gradient. So, the gradient, if you remember, was y times cosine x y comma x times cosine x y, right. And so, if we put this in, this is y times cosine x y comma x times cosine x y dot with u, which gives us u1 times y times cosine x y plus u2 times x times cosine x y. Okay. Very easy to compute. Now, again I will ask you to go back and try to do this from first principles to compute the directional derivative of sine of x y. In fact, we started doing this in our directional derivatives video, and then I stopped at some point and suggested that you do it because it became fairly tedious, and also I wanted you to check the answer for yourself, and now you see if it matches with what we have here. Okay. So, I hope the tediousness of the computation for the directional derivatives is no longer an issue. If you are bothered in when we first computed directional derivatives, that this is a really difficult thing. I hope that now you will feel that this is no longer difficult, and that this is actually something very easy. Of course, the main idea is to use the gradient vector, and so there is one small warning, and the warning is that the hypothesis over there has to be satisfied. And so I want to do this final example of f of x y is x y by x squared plus y squared if x y is not the 0.00 and it's 0 if it is the 0.00. We have computed already what is the gradient for this. So, the gradient for this is so x cube minus y squared x by x squared plus y squared squared, which I could have taken out, and y cube minus x squared y by x squared plus y squared squared if x y is not 0 and it is 0 if x y is 0. Okay. So, this was a computation we did, the gradient computation we did a few minutes ago, and that was dependent on the partial derivatives, which we have computed in the partial derivatives video. So, in the directional derivatives video, we computed the directional derivative at 0. Let us see what happens for the directional derivative at any other point. So, if your point is not 0, both these functions x cube minus y squared x by x square plus y squared squared and y cube minus x square y by x square plus y squared squared are continuous. Why is that? Because they are rational functions and the denominator is non-zero. So, once that happens, we are assured that they are continuous, and so we can apply the result that we saw on the theorem that we have seen in this video. So, this is just gradient f at x y dot with u. So, this is if x y is not 0, right, which tells us that this is u 1 times u 1 by x square plus, okay, let me rewrite this, 1 by x square plus y square times u 1 times x cube minus y squared x plus u 2 times y cube minus x square y. This is what the directional derivative is if the point is not 0. So, notice how that theorem allowed us to avoid all the difficult computation with limits. What happens at 0, and this is the real cautionary tale here. So, at 0, we actually computed what happens, and what we got, if you remember, was that this is u 1 u 2 by h. So, this is 0 if u 1 or u 2 is 0, which means it is in the direction of the x axis or the y axis. So, those are the partial derivatives. The partial derivatives are 0, which we have in this from here as well. But if it is not, if that is not the case, then this does not exist, right, because this is a limit of 1 by h or some constant by h, and so this does not exist. And so, this formula for the gradient, so the gradient dot u will give you the directional derivative, does not hold in this case. And what went wrong? What went wrong is that at 0, the gradient function here, so this gradient function here at 0 is not continuous, and this is actually something we checked in our video on continuity. So, I will again suggest you go back and check that we have actually seen both of these functions are not continuous at 0, and we have seen in continuity that for a multivariable function, meaning a vector valued multivariable function to be continuous, each of its component functions have to be continuous. In this case, neither of them are continuous at 0. So, this is not continuous at 0, and immediately the theorem fails to, so we cannot apply that theorem as a result, and so we have this situation where the partial derivatives do indeed exist and are 0, but the directional derivative does not exist. So, it is not given by gradient dot u, which would otherwise have been 0, right. So, so you have to be also careful when you apply that theorem, and there is a hypothesis lurking in the background. If you are lucky and your functions are nice, you do not have to check that, and for this course that is most of the time that is what is going to happen. But if you do math in particular, you do have to worry about such details. So, let us recall quickly what we have seen in this video. Very importantly, we have seen what is the gradient function or the gradient vector. It is a very easy function, you just put together all the partial derivatives into a vector, that is all it is, but it is a very important quantity, and it is going to show up later on in this course as well as other courses. And the main punchline was that we can use that to compute the directional derivatives with some hypothesis, as the gradient vector dot with the vector u, the unit vector u in whose direction we are taking the directional derivative. Thank you.